Hello, my name is Jared Coleman, and today I'll be talking about our work on minimizing the maximum distance traveled to form patterns with systems of mobile robots. First, I'll describe the problem we're interested in. Given a set of robots initially deployed arbitrarily on the plane and a pattern, we want to find the destination for each robot so that after every robot arrives at its destination, the system forms the desired pattern and the maximum distance traveled by any one robot is minimum. As you can see, there are many valid solutions for a given pattern. The question we are asking is how can we form the desired pattern by moving the robots as little as possible? The pattern formation is a broad problem and has many variants that have been studied extensively in the past. Previous work in pattern formation, however, is mostly concerned with finding which patterns are formable. Our study draws upon the work of previous researchers in possibility results. Other studies have offered solutions for specific variants of the pattern formation problem, including uniform circle formation, forming a ring, gathering, bio-inspired swarm formation, and also fixed destination formation. We draw upon previous work to study the more general, optimal pattern formation problem. A little bit about notation. We use lowercase letters for points, the function d for Euclidean distance, c for a circle with radius r centered at P, and d similarly for a closed disk. We use capital letters for sequences of points. We call two sequences rigidly similar if there is a translation, rotation, and/or uniform scaling of one that would make it equivalent to the other. Two sequences are similar if they are rigidly similar by some reflection or permutation. Our primary goal is to find a globally optimal solution, regardless of model. We show also that the globally optimal solution is achievable under some, but not all models. We consider models that are globally coordinated if they have access to a global coordinate system, oblivious if they do not rely on any system state, synchronous if robots move in lockstep with each other, and oriented if they share a common sense of north, south, east, and west. Previous research in this area has shown that an optimal solution is not achievable in many of these models. We show that our solution is invariant to obliviousness and that it's valid as long as robots are synchronous and either globally coordinated or oriented. The layout of this presentation is as follows. First, we will discuss the necessary conditions that every solution must satisfy in order to be valid. Then, I'll introduce replication, a geometric tool that is used to prove the correctness of our main results. After presenting the main results of our study, I'll show that they lead nicely into a metric for comparing arbitrary triangles. Finally, I'll show some interesting properties for specific triangular patterns and wrap everything up with a short conclusion. First, we show that in any valid solution, at least 3 robots must move the maximum distance. We prove this by contradiction, showing that if only 1 or 2 robots moves the maximum distance, then we can translate, rotate, and/or scale the pattern to achieve a better solution. Replication is a tool based on pure geometry that can help us reason about systems of 3 robots. We define the trivial replication as the shape achieved by fixing 2 points in the pattern to 2 points on the plane. In this case, our pattern is a right triangle, and we fix the most acute point to U and the second most acute point to V. As you can see, this leaves the point associated with the right triangle at a determined point on the plane. We call this point, or C in the figure, the trivial replication point. Next, we define the replication machine. This time, we consider the set of all shapes similar to the pattern with one point fixed and the other bound to a circle. Observe how the set of all trivial replication points form a circle given by this formula. We call this the replication machine circle. Finally, we define the replication spanner, in which we fix 2 points of the pattern to 2 circles on the plane. Observe how the set of all trivial replication points are bounded by a circle, given by this formula. We call this the replication spanner circle. Now, I'll show how we can use replication to find the optimal solution for a system of 3 robots to form any pattern. Let the black vertices be the initial configuration of the system, and the blue vertices in the upper right corner be the pattern they must form. In this example, they will form a 30-60-90 right triangle. First, we index robots and patterns so that smaller angles are assigned smaller indexes. Then, we normalize the side length of the pattern so that its perimeter is 1. Then, we find the trivial replication point T0 by replicating the pattern on R1 and R2. Then we claim that robot R0 should move a distance toward T0 proportional to the length of the side fixed in the trivial replication. In other words, R0 should move exactly 1 over 3 plus the square root of 3, or a little bit less than a third, of the way towards T0. This destination point is Q0. Similarly, we find the trivial replication points T1 and T2 and the destinations Q1 and Q2. First, we show that all robots move exactly distance d star from their initial position. Then, we prove that the shape that Q0, Q1, and Q2 form is similar to the desired pattern by observing that they lie exactly on the intersection of the replication machine circles. As you may have noticed, the solution to the min-max pattern formation problem depends on a kind of distance between the original and destination triangles. By itself, though, this isn't a valid metric for comparing arbitrary triangles, since it's dependent on absolute position in the plane. In order to create a metric that can be used to compare any 2 triangles regardless of position, orientation, scale, and reflection, we need to modify our algorithm just a bit. Suppose we have 2 triangles indexed by increasing interior angle. Then, consider the trivial replication of each on the points 0, 0, and 1, 0. Then our metric, tau, is the distance between the 2 resulting trivial replication points, which can be written as so. As you can see, tau is a function of only the interior angles of the 2 triangles, not any embedding onto the plane. Tau satisfies all the necessary properties to be a metric. Just to demonstrate a potential use for the metric, consider these 20 randomly generated triangles. We use the metric to sort these triangles by their tau distance to the equilateral triangle. This is essentially a measure of how close to equilateral a triangle is. Finally, we show some interesting properties for systems of 3 robots. The first is that for any optimal solution, all robots move either toward or away from a single point in the plane. We call this the focal point. Another interesting property is that if the desired pattern is an equilateral triangle, then the center of the mass of the system is constant at all points in time while the robots move to their destinations. One important property is that the optimal solution is invariant to obliviousness. In other words, the solution does not change as the robots approach their destinations. In this study, we started to develop a theoretical basis for the general pattern formation problem. We also proposed an optimal, purely geometric solution for systems of 3 robots and demonstrated how it could be used as a metric for comparing triangles. Future avenues of research including solving the problem for the n-robot case and exploring applications for the proposed metric. Thank you for your time, and I hope you enjoyed this demonstration of our work.